Okay, so now let's bring all this to a close and tie a nice little bow on this equilibrium constant. Let's go back to the example where we talked about David's becoming Dana's. And if you remember, David's became Dana's by rolling a 1, 2, or 3, and Dana's became David by rolling a 6. So, therefore, we got that. Okay, so if you remember from previous videos, we made this equilibrium expression right here. Boom. And we basically said that the equilibrium constant is equal to the concentration of Dana particles over the concentration of David. Well, I'm going to now take this guy and I'm going to say, okay, at equilibrium, which is what most predominantly? Oh yes, we already decided this. It's 75%. If I were to average all of these guys, it's going to be like right at 75%. What does it mean to be 75% in this example? Well, if it's 75%, then that means there's 3 Dana particles for every 1 David particles. Oh, wait a minute. So you're telling me that the equilibrium constant, I could figure it out. It'd be 3 Dana particles for every 1 David particles. Therefore, the equilibrium constant for this reaction here is 3 to 1. What does that mean? Does that mean that the rate of going from one to the other is 3 times greater? Oh, no. Think equilibrium. Equilibrium is when the rates are equal. What that means is there are 3 times more particles at equilibrium in the Dana phase than there are in the David phase. And that is what the equilibrium constant tells us. If that number is 3, then that means it's 3 times more in the products than it is in the reactants.